In this video, I'm going to talk about laser. Perhaps the most familiar laser that we know is a laser pointer. So, a laser pointer these days comes in many shapes and sizes. Can be as small as something that hangs on your keychain, or it can be something that looks like a piece of whatever rod or disc that you hold in your hand, and when you press it, a beam of laser light is emitted. Yeah, that's my laser pointer, and that's my laser beam, and then you would point this beam maybe on the board if you're doing if you're a teacher teaching a class, or you might point it at other people just to have some fun. Okay, but try not to point at someone's eyes. Okay, you can actually damage people's eyes if you're not careful. So this is probably the most familiar laser that we know these days, because everyone can buy one very cheaply and play with it. And the most obvious thing that we know about the laser from this kind of toy that we might get is that the laser beam goes in a very narrow beam, and it doesn't spread out. So you can shine this at, say, the other end of the room, and you see a tiny spot on the wall. Okay, and that is very unlike using a torchlight. Let's say if I have my everyday torch where I put some battery inside and there's a light bulb here, then this torchlight would give out light when I switch it on, and this light would just spread all out. If I shine this light at the wall, I get a huge spread. Obviously it's different. Obviously a torch is different from a laser. So the most obvious thing that we notice, that we know about the laser beam, is that it is really narrow, and it stays narrow for a very, very long distance. Okay. Now, so in this video, I want to talk about a few features about laser beam. One of the features is that it has a very narrow beam. Okay, very narrow beam. Now the other one is how it can be very useful. For example, it can be used to, say, use in a DVD player. And it can be used to cut metal. Right? We don't see laser being used to cut metal every day. It's being used in some factories in some countries or some parts of the world, but you might have seen laser used to cut things in movies. So it's fairly familiar from movies. And DVD player, we might have all seen, used, or heard it. And inside the player is a tiny laser that is hidden. So I'm going to take a look at these and try to get an idea about why a laser beam is useful. Is able to have all these features. So let's start by thinking about why, how a laser beam, how the details of this light come out from laser beam, how is it different from a torchlight? For example, can I not, just get a piece of, just put a piece of paper or metal here, make a small hole down here. Can I not just do this and get a straight beam coming out from here? And that, wouldn't that be a laser beam? Well, we can try, but the likelihood is that you'll find that it would quickly spread out a lot more than laser beam. The reason for this is because this is what we call an extended source. It's a source of light that the source itself is already quite spread out. Right? So it's already quite spread out, and the light comes from, if you like, if you think that this is a filament lamp, a filament light bulb, it comes from everywhere, all the different points in this filament, and there's some light going in all directions from every point in the filament, and as a result, even as it comes out through that small hole, okay, you have light going that way, light from the top of the filament coming down, so it's already spread out and going out in all sorts of directions, even though you make a small hole. And then you might think, okay, so even with a small hole, I have light spreading out quite a lot. So why not, put another piece of metal here with a small hole and block all this? Yeah, we can do that. But if you do that, you are going to cut out a lot of light. Like the first piece would already cut out a lot of the light. The second piece of say metal or paper would cut out a lot more, and in the end you might get it would actually be possible to get a very narrow beam if you try maybe 1, 2, or maybe even 3, right? Just to make sure that all those spreading out get cut off. We might actually be able to get a very narrow beam, but by the time you've cut off all the rays that are spreading out, this becomes very weak. It becomes very weak. So there's no way it can compare with the laser beam in which all of the light, right from the start, in which all of the light is already going in the same direction. So that's one thing. Now the other thing is that this idea that the light is going out all in the same direction, we also need to understand this in terms of the wavelength. Now, for example, we know that laser is light and light is wave. Okay, so if you look at, say, a small cross section of this, we might imagine that this laser beam has a certain width. I mean, if you have actually played with a laser pointer before, and if you shine it on your hand, for example, you'll see a small spot. It's not that small. It's not like a very tiny point. It might be around 1 or 2 millimeters even, depending on the laser, or maybe half a millimeter. Right? So it's a visible spot that falls on your hand. So let's say it's about 1 millimeter. Now, if it is about 1 millimeter, that is like, as I explained, that is like having maybe light going through a 1 millimeter hole in a metal sheet. So what comes out is also 1 millimeter. And we know what happens when we do this to a wave. So let me just remind ourselves of what happens if we have a wave. Now, if we have a wave, if we have a wave coming through a little hole, it will diffract. There will be diffraction. Surely this wave will spread out. So if I look at any particular point on the laser beam, shouldn't it spread out because it is a wave? Indeed it should. Indeed it should. But remember that for the spreading out effects to be quite obvious, that means as big as maybe many degrees, not just less than 1 degree. For it to be many degrees of spreading out, this gap, this hole, must be comparable to the wavelength of light, maybe a few times the wavelength at most. Okay, then it will spread out very obviously. Now, but if you're talking about 1 millimeter here, if you're talking about 1 millimeter, compared to the wavelength, right? In the last video, I've talked about the wavelength of visible light. So you might remember that for, say, red light, the wavelength is about 700 nanometers. So 700 nanometers, we're talking about not millimeters, nanometers. Okay, we're talking about less than a micrometer, which is less than 1,000th, less than 1/1000 of a millimeter. So the wavelength is tiny. We're talking about a width, a 1 millimeter width, or if you imagine here, we're talking about a slit width, or hole width, which is 1,000 times bigger, than the wavelength. If we have such a big hole down here, then there would be very little spreading out. Right? The amount of spreading out would be very little, which is why the laser beam, if all the waves are going in the same direction, which corresponds to plane wavefronts, parallel wavefronts like that, all the waves going in the same direction. All the rays going in the same direction, which corresponds to plane wavefronts, then the effect of the diffraction of the wave property of light here would be very small. Now, there's actually a way to estimate how much it spreads out from a single slit. Now, I've not actually talked about a single slit diffraction, or at least the calculations of that in my earlier videos on waves. But I've talked about diffraction grating. Right? If you remember, I've talked about diffraction grating, in which there are many slits, and that the diffraction of the light gives rise to the interference between wave coming out from different slits gives rise to fringes, in which the angle is related to slit spacing. Okay, and it's given by d sine theta equals to n lambda. So in the first fringe, for example, n is 1, this formula tells us what this angle is. Now, using this formula, okay, we can get a rough idea of how much the spreading would be from a single slit. Quite simply by thinking about how we can get this fringe in the first place. Now, in the first place, we can get this fringe only if the light going through each slit, right? The light coming out from each of these slits actually spread out, actually bend enough, right? So bend, by maybe this angle or more, so that they can all interfere in this direction. Okay, so by this very condition, and by the fact that it has been observed experimentally, we know that this same angle that we can get from this formula gives us a rough idea of how much the beam can spread out. because at least the beam must be able to spread out until it is more than the angle for the first fringe. Alright, so that gives us an idea. So I can actually use the same formula to estimate how much it spreads out. Okay, so what I can do is, for example, if let's say it doesn't spread out very much, I can say that if angle is very small, then I can say that sine theta is approximately equal to theta in radians, and this is in radians instead of degrees. So if I'm talking about just the first fringe, then this formula becomes d times theta. Sine theta is then theta. It's approximately lambda, and that gives me a very useful and simple relation where I can estimate theta if I know lambda and d. Okay, so if let's say the amount of bending is theta, then according to this formula, then theta is just lambda over d. Theta is about lambda over d, where in this case I'm going to take in this case d would be the slit spacing. Okay, so what I'm doing here is a very rough formula. I'm doing a very rough estimate, because after all I'm talking about the slit width here, but the d here is actually the spacing between slits. Okay, but the formula roughly works. So using this formula, I can estimate the angle that the laser beam from my laser pointer will spread out if the width of that laser beam is about 1 millimeter. So let me try that. So in this case, my theta spreading out, this is about lambda over d. So if I'm going to take that as my d, 1 millimeter, and that's the lambda for red light. So just to make things easier, I'm going to take this as roughly 1,000 nanometers, which is 1 micrometer. So I'm going to do lambda over d. I'm going to do 1 micrometer divided by 1 millimeter. 1 micrometer divided by 1 millimeter, and that gives me 0.001 radians. So in radians. So this means that as it spreads out by this kind of angle, and let's think about how this relates to, say, the laser spot that we see on the wall. If we shine this on the wall, let's say we're standing about 1 meter from the wall, when we shine that laser beam on the wall, we get a very sharp spot. So how much has that spot spread out from our laser pointer? So let's make an estimate based on this. Now the spreading out, now how do we use this angle if this is in radian? Well, let's just recap a little bit of how radian is defined. If I have an angle that is in radian, okay, what we can do is we can draw these two lines that contain the angle to a length. If I think about the length as r for each line, and I think about drawing an arc, joining these two ends centered at this corner here of say arc length s, then the radian is defined by arc length over r. So the angle in radians would be arc length over r. So this gives me a way to find this arc length. Alright, it means that s, the arc length is equal to r theta. So if you imagine that this spreads out by an angle theta, okay, let's say this spreads out by an angle theta. Say this angle here is theta. Then the beam spot, which was which has spread out until here. Let's say it has a certain width here, and that, if you compare with this picture, the width of this beam spot is roughly just the arc length. If you imagine that that's the center of my circle, or you can take that as the center. So if I shine this for a length of about 1 meter, right? Let's say this travels for about 1 meter to the wall. So I can take this as my radius 1 meter. then all I need is to multiply the radius by the angle, the radius by this angle, and I can get the size of the spot on the wall. Okay, so let me do that. The size of the spot on the wall is S equal to r theta. So r is the distance to the wall, which is 1, and theta is 0.001 radian. And the answer is 0.001 in meters. So meaning 1 millimeter. So if I'm standing 1 meter from the wall and shine this laser beam at the wall, by the time the laser beam reaches the wall, the beam spot would have spread out by 1 millimeter. Meaning that if it's originally 1 millimeter wide, when it just come out from the laser, when it reaches the wall, it's about 2 millimeters. Okay, so that's a tiny spread compared to if you use a torchlight where the beam just spreads out into a huge spot, or maybe as big as 1 meter, and it reaches the wall. So in this way, we can understand that, we can appreciate why what we would call the laser beam can actually remain narrow for a long time. And the reason is because I've been describing this in both two ways. I've first described this as because all the rays are going in the same direction, and then I switch over to the wave picture, in which I drew wave fronts that are parallel. Okay, and what this means is that over, say, this wavefront, or over any cross section of this beam, right, we have a uniform wavefront, meaning that at every point along the cross section, or along the slit, or along, say, a cross section of the beam, at every point in the cross section, the wave is coherent. They are in phase. So if I look at a wavefront that is parallel, it means that at this point, this point, this point, this point, along this cross section, the wave is always in phase. Right? If it's a peak here, then it's all peaks along here. If it's a peak, if one of the rays is a peak at this position, then all across the cross section of the beam, at every point in the cross section, the waves are in phase. So we describe this by using the word coherence. This is a coherent light source, right? Where the cross section, the points along any cross section is always in phase, right? If they're always either all peaks or all crests, or all troughs. And because of this, we have seen that we can use the idea from diffraction grating to estimate the formula for diffraction grating, to estimate the angle at which it spreads out. And we've seen that the amount that, say, a laser pointer beam will spread out when it goes to the wall is very small. It's only about 1 millimeter. And you can imagine shining it, say, to the moon. Okay, if you multiply by the distance of the moon, you find that when it reaches the moon, it might spread out to maybe just a few hundred meters. Okay, so the spread is that small. Now, having such a very small spread means that we can use it as a laser pointer, obviously. But why can we also use it for a DVD player and to cut metal? Now, the reason is because having such a coherent beam also means that you can focus it into a really, really small point. Now, if you have a magnifying glass, we know that we can focus sunlight into a small point. And if you have ever played with a magnifying glass, in which you focus, say, light from the sun onto, say, a piece of paper. Right, if you have ever played with this, right, be careful if you do. You can see this spot on the paper starting to turn black and maybe even catch fire. Okay, so we know that this is what can happen. And that's exactly what is done to a laser beam that is used to cut metal. The very coherent beam, in which all the rays are very parallel, are being focused onto a tiny spot. Okay, so as a result, the power, the intensity at that at that tiny spot becomes so high that it is able to melt metal there. This is a piece of metal and this is a laser beam. So that's why it can be used to cut metal. And for similar reason, it can be used in a DVD player, because a DVD, you can't see it with our eyes, but actually contains very tiny holes, right? It contains tracks of tiny holes or tiny pits of different lengths. Again, the different lengths of the pit contain some kind of a code that contains our music or our video. Alright, so when the laser light gets reflected from the DVD, our DVD player will play back our music or our video. And because the laser beam can be focused onto such a tiny spots, the data tracks on the DVD can be made extremely small as the wavelength of the light, right? Which is why a lot of data can be contained on a DVD. Maybe if you have ever bought a recordable DVD to record your data, you know that these days, as in now is the year 2014, alright, if you still buy DVD, if you still buy DVD recordable or rewritable, you'll notice that it's usually about 4 point something gigabytes of data that you can write onto a DVD. And it's because it's possible to focus the laser light into a very tiny spot of about the size of a wavelength.